Thank you all for joining this session. So this is joint work with Boris, Andrew, Shruti, Lukas, and Santiago, all from various research teams at Microsoft in Cambridge. And this work is about showing, this will be really the main takeaway, it is about showing that we can prove the security of training algorithms for machine learning models, such as DP-SGD, without the interaction through differential privacy, which is kind of odd given the session we're in. And the way things work usually is we start with a training algorithm, and then we prove that it satisfies the differential privacy notion, meaning we bound its information leakage and any sort of leakage. But then in practice, all we care about are specific attacks, so how secure our model will be against specific attacks. And so what we need to do is we need to go from differential privacy and our parameters back to, and match them to the whatever security notion we're interested in. And this may be hard, for sure, sometimes potentially inefficient. And so really, the whole purpose of our work here was to see whether we can avoid this interaction. And we'll take a look at record-level inference attacks. So this means that the attacker is interested in inferring some property about the data record that was used for training a model. For example, attribute inference. In attribute inference, the attacker is given a data record with one missing value, which we call the sensitive attribute. And their goal, given access to the model, is to try and make a good prediction for this value. On the other end of the spectrum, we have membership inference, where the attacker is given a data record, but this time the model may or may not have been trained using that particular data record. And the goal of the attacker is to decide which is which, so whether this data record was used for training. So record-level inference somehow generalizes this, and as I said, the attacker is interested in discovering some property about a specific data record, and our goal is to measure, what's the risk that the attack will succeed. And to measure this risk, we use the notion of base security metric. So intuitively, base security measures somehow the delta between the risk before releasing the model, so the risk that the attack will be successful with the attacker just using prior information, any prior information they might have. And we measure the delta with respect to the risk after releasing the model, when the attacker sees it. And so its value is 1 when there's no delta, meaning the risk before and releasing the model is the same, so we might as well just release the model. And it takes smaller values if indeed there's some information leakage. So you may be wondering, well, do we really need to create a whole new metric just for this work? No, we're not really creating a new metric. Base security is just a simple generalization of the concept of advantage, which is widely used in inference attacks. And the reason we use it is that, well, it makes our math easy. It makes proving these sort of statements quite easy. And the second reason is that we can match it back onto security metrics that people tend to care about, such as the attacker's accuracy and TPRs as FPR, and we can even match it back to differential privacy loosely if you really wanted to. Finally, and this will be important, base security can be reduced to computing the total variation between two distributions, and this will be useful later. So in the very short time, I wanted to give you a high-level idea of the proof behind all our statements. And the main idea is really to look at the DP-SGD algorithm, this training algorithm for machine learning models, as if it was an information theoretic channel. And this channel takes as input the data record. More formally, it takes as input whatever property the attacker wants to guess about the data record. And then the channel outputs whatever the attacker is able to see. And in our work, we assume the attacker can see all the intermediate gradients that were computed for, intermediate noisy gradients that were computed for that data record. And then, given this noisy channel, our goal is to understand how much information leakage there is intuitively. So, given this setup, all we need to do for computing-based security is the following. We need to look at all the possible values of the property we're interested in, and all the pairwise values. And then we run them through this information channel, which means literally we run DP-SGD. And this is a noisy channel, so we get some probability distribution as output. And of them, we compute the total variation distance. And of course, we do this for all the pairwise values, and we look for the two that are the easiest to distinguish, and that is the ones that maximize total variation distance. So, concrete example for attribute inference, we start with a data record and we have one sensitive attribute. What we do is we replace the sensitive attribute with all the possible values, right? And we check which two are the easiest to distinguish. So this is the plan. Now, we should have everything, right? We know how to compute this base security. All we need to do is we need to specify the distribution. And I'd like to bring to your attention that up to here in the analysis, we made no particular assumption about DP-SGD. And the reason is that this method really can be applied to anything. All that changes is the output distribution. So what's the output distribution? Well, for one data record, DP-SGD, what it does internally is, first it decides whether the data record will be included or not in our batch. And then it computes its gradient, and then it adds some Gaussian noise. By this process, what we end up with is a mixture of two Gaussian distributions. One that is centered intuitively around the gradient of the point, and the other one is centered at 0. It represents no contribution for the point because it was not sampled. Cool, so you'd think theoretically we're done pretty much, like we know exactly the process we need to carry out. We know the distribution, we can characterize it fully by the gradient. Well, the big issue, and this is an actual quote by Larry Wasserman, is that mixtures are terrible creatures and they're very, very hard to deal with. And so I'm not sure about the tequila statement, but this is definitely true about mixtures. And so, well, what we did is we took his advice and we avoided the mixture distribution. And so the very main trick of our proof is to approximate the Gaussian mixture with a Gaussian. Now, if you look at the two, you may be a bit surprised. You'd be like, what? I mean, they don't look nearly the same, right? One distribution has 2 peaks, the other one has 1, right? Very luckily, we were very lucky in this case. So in DP-SGD, we have a privacy parameter, a noise parameter. And the more noise we add, the more the mixture actually tends to have 1 peak. And so you will find that the more privacy we add, the better this approximation is, which is super convenient. And so we did. And so when we do this approximation, then we can apply some nice results from the 80s and get a good result that holds for any record level inference attack. What do we do with this? First result for membership inference, we get a closed form expression for the risk against membership inference with respect to the DP-SGD's parameters. So how does this compare to existing analysis? And the DP-SGD space has been flooded by extremely impressive results, honestly, on membership inference, right? And the state of the art is actually tight. There is absolutely no way we can improve on it under the current assumptions. So we actually do match the state of the art. We don't improve upon it, but we do the same. We do this with a speed up of orders of magnitude, because we can compute it immediately. And so the fun thing we could do is we could publish this interactive web page where you can play around with the parameters of DP-SGD and calculate the security of your model. Now, for attribute inference instead, I think we did something even slightly more interesting. So for membership inference, we made an assumption of worst-case gradients. For attribute inference, we actually started tracking the values of the gradients while we ran DP-SGD. And we ended up with a data-dependent analysis for it. And by doing so, we actually got extremely massive improvements with respect to membership inference. Attribute inference is a much weaker kind of setup. It should be easier to defend. And in addition, we're doing a data-dependent analysis. This means we know exactly for a particular data set how much secure we are against that threat. And so, for example, if you wanted to train this model with 60% accuracy, and you cared about membership inference, I wouldn't recommend you to publish that model. But if you only cared about attribute inference, then you could easily do that. Cool. I think there's just one takeaway message. I think there is a lot of value in looking specifically at threats rather than at general definitions, I guess, of leakage. And it can be advantageous, both numerically, but also in terms of communication, I'd say, and interpretability of the results. So thank you for listening.